right. So we just wanted to kind of give a quick intro to the long span post tension parking structures, just to kind of get you introduced to it, and get you thinking that it's possible for anyone. I think anyone in our company to design one, and not be scared of it. So this is the secrets of long span post tension parking revealed. What is long span post tension design? It's a typical beam and a typical slab. It's a one-way slab. We usually do 5 inches, 5 inch thick post tension one-way slab. Some other firms do, like a 5.5 inch slab. And then the beams are a standard beam, which comes from a form system. It's sometimes called a Cunningham beam. These are post tensioned, and they are 14 inches at the bottom and 16 inches at the top. They're tapered slightly you can see our typical detail, and they are 35 inches deep from the top of slab. There's a small picture to the left of kind of the typical slab span, and then the beam kind of running right to left here. Then just a couple other shots. So the green is a typical tapered PT beam, and then on the right is kind of a top shot of the T section with the PT strands in green, and then your ties and your kind of minimal top and bottom reinforcing. Then you can see the one-way PT slab tendons in green running transverse to the beam tendons over the top. So just some kind of typical rules of thumb for this system, the Cunningham PT beam, is that they are typically right around 62 feet, and then there's a little bit of a range of 60 to 66 feet range, and this is based on, you can kind of see in the little architectural image down here that it's based on one stall here, and then a driveway, and then another stall over here. So that's where this typical 62 foot comes from. And then your beams span from this grid C to grid B. And then this beam spacing is generally in the 17 to 19 foot range, which is two stall widths. And these dimensions all vary slightly by kind of jurisdictions and where you are. So some of them have like they have an extra inch or an extra 2 inches to some of these. So sometimes these, this becomes like 17.4 or something, and then we got typical gravity columns aligned with, each PT beam, each grid. And, generally we're using 24 by 24 gravity columns. And so this is the architectural floor plan. Then this is the typical structural framing plan for that same floor plan. So here's our PT beams, roughly at 17 feet on center. And then our 5-inch slab, do we call it out? A 5-inch slab running it spans 17 feet, and it's one-way PT. And so these black arrows are our typical tendons. So this is our slab tendons. We call them out as kip per feet, so we don't call it the spacing. You can do that. You can kind of do either. And then we have all of our beams labeled B1, B2, B3, B2, B1, and then we have a schedule for all these beams. This is our, the simple, typical layout, and spacing and spans. And then over here, this is 124 or 5, I think. So this is like about 62 feet, 62 and a half, which goes with our typical spacing. And then the loads, we're in California, so we're going off of CBC. So the typical garage floor loading is 40 PSF. Sometimes some people think it's light, but it's for for traffic. And that's straight from the code, and that's non-reducible for the floors. There is an exception for the section for members supporting more than 2 or more floors. So let's say a transfer girder or columns or footings, you can use a 20% max reduction for your live load. Otherwise, for your floors, you're doing 40, and that's it. You're not doing any reduction. And then we have these vehicle barriers that those are your 6,000 pound concentrated. It's kind of like an impact load at 2 feet 3 inches high. So for instance, here's one of your barriers. And then your floor load is pretty minimal in addition to just the self weight. So between here to here, you have your 5-inch slab self weight, and then you have a little bit of piping, and then a little bit of miscellaneous. So that's it. So usually we're adding 2 PSF additional dead load for your mass of the slab. Then you have your columns, beams, etc. But for the slab itself, just 2 PSF additional. And then the simple, easy design, there is 3D software that you can do this. But the simple, easy design is you do 1 calc for a slab and you do 1 calc for a beam. And it's all in this ADAPT PT, ADAPT PT RC, it's called, and you're using the PT portion of it. So here's kind of the little interface of it, and here's your options: 2-way slab, 1-way slab, or a beam. So for this PT long span parking garages, you're doing one of these and you're doing one of these, and that's the majority of your gravity design. It's just two of them. Then there's repeats. For instance, here's a little key plan I did for slab design. So I have this one slab design here. I have another one here, S2, S3, S3. And so maybe you're doing like 5 to 6, 7, 8 slab designs for, this is a 9-story parking structure. But they're all based off of one slab. You can do one and then just copy the rest, And then for your beams, there's so much repeating. You can see, all of these they're all the same span. They're all the same spacing. There's a little bit of unique conditions like this, you have a little bit less load on it over here. But for the most part, you're doing, one slab design, you're doing one beam design, and that's it. And then with some minimal modifications. And so with this ADAPT software, there is tutorials and literature to read about this to get up to speed. And then I think if you're ready to get into design of one, I think you can get a quick intro to learn about some of the typical PT post-tension stuff, about draping, the amount of forces, your balance, your dead load balancing. I think fairly simple with some kind of internal design guides that San Diego's created as well. And then then there's other stuff with like mild steel, cord reinforcing, temperature shrinkage tendons, in addition to just the post tension tendons for the slab and the beams. So here's just a couple other shots. There's this one on the left is your typical post tension beam, and then your typical beam has 12 tendons for this 62-foot span, 17 feet on center spacing. So let's see if we can count them here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There you go. And then here's a zoomed in view looking inside the beam before it's poured. So they're all kind of bundled together, and they're sheathed in these little casings, so you can tension them after it's poured. And here's a cage and some typical bottom bar. And then so we have our typical PT beams that have 12 tendons. They're 1/2-inch diameter, 270 KSI ultimate stress, and then they have a final effective force of 27 kips after some relaxation and friction losses. And then our PT slab, which you can kind of see in one of our other slides, was it's usually one of these same exact tendons at 3 feet 4 inches on center. And these are all typical. So after you do your calc, you should be getting this, and the same for the beam. So there's a lot of repetition from one job to the next, And then, so here's an example of our beam kind of a schedule and little elevations showing, the reinforcing detailing, the draping of the tendon. And so we have our A and B and C distances, and then so this tells them how to drape the tendon. So on the bottom it comes down to, in mid-span it comes down to the low point, so we have 3.25 inches here. And then we have our PT force. The PT force is the total amount of force. So if we have 27 kips per tendon, you could take one of these, 290 or 320, and divided by that 27, you'll come out to 12 tendons required. So this is kind of how we typically set up. Then we have our reinforcing. This is how we typically set up our beams. So in the schedule and low elevation. Then we have others of these as well for multi-span or some unique situations that are already set up. But this is our typical one span elevation. And then so for California, we're typically looking at moment frames and then sometimes shear walls. I'd say majority we see moment frames, but then the shear walls, we have done some studies, and if they can get the shear walls to work, we have found that they are cheaper. So here's a typical moment frame system, and it kind of this is our structural elevation, showing here's all our frame sizes. I mean our frame call outs, and then in between here, this is a non-frame section. We just have crash walls here, and then some more frames over here. So we'll do this on each exterior side, and the moment frames are just generally on the exterior of the building. And then here is a typical concrete shear wall, kind of the same thing. Here's our structural elevation. So then all these other bays are just crash walls. So we have our concrete shear wall here, and then everything else. So there's less lateral system. And then here's an image of it. So here's our concrete shear wall, and there's one kind of tucked behind this little elevator landing. And this one was unique, as they can use this as kind of an architectural feature, and they put some like kind of an art installation on this type deal. And these look like moment frames, but these are just crash walls. So they're minimal and they're not connected. I'll touch on that later. And so we generally see these on all four sides as well too. Sometimes down the middle, and then we're usually putting their shear walls in the middle to help with shrinkage, so everything's not constrained. We do also have pour strips too that I'll just touch on briefly, but that is to divide up the length of the slab, so you can so you have enough. You can't tension your tendons for a very very long length over. I don't know what the rule is. It's 100-something feet, and that's for your losses, your friction and your final effective force losses, and to allow for shrinkage of the slab. So this other part I was touching on is our typical crash wall when you don't have a moment frame. So it's usually just a small 6-inch concrete wall, and it's kind of a little tricky. There's kind of been some debate about this and some articles about developing this. We use a number 3 bar so we can kind of develop it into the slab. This gets thickened a little bit at the edge, so this is actually 7 inches. But this is our typical crash wall detail at the ends of the parking structure. And then these are never connected to the columns. There's always a gap here. That's so there's no force attraction here, and this rips apart from the wall, or some kind of little captive column type deal. Then otherwise you can do moment frame beams act as your crash wall, or also cable barriers, and sometimes these are in the interior and then these are on the exterior, or the cable barriers can be used anywhere as well though too. So here's a couple more images of the crash walls, and you can kind of see the joints here at each end. So there's that little gap, so they're not inducing any moment into the crash wall. And then here's the same elevation, and then so here's our number 3s at 6 inches on center, and then they'll do the little gap each side. And you can see that here's our post-tension strands. Here's actually a transfer girder that we did post-tension. And then here's our typical columns, 24-inch square typical columns. And this is a 9-story parking structure. Then some additional topics. There's some unique non-bearing wall connections where you want some top slip connections, and then also each end of the wall not connected as well, kind of similar to the crash wall. We have some typical details for when it transitions from a slab on grade to a PT slab. And then there are some areas where there's kind of overlapping tendons. We have typical details for, and tell them and to say which tendon controls over the other and where does it go, above or below, etc. There's some unique PT girder situations where, for instance, we can see this one right here where we have full level columns landing on a girder. So this is post tension beam, and then also on the interior, for instance, here where there's one column, interior column missing. You take one out, then you have a double span girder. So there's one column missing. So there's a girder right here. So you usually have a couple girders per job as well. Then there's unique load balancing. So for the post tension slab and beams, where you want to balance a certain amount of the dead load. And there's different values for slab and beams. This is all in literature and some of our kind of design guides too. There's some unique stuff about fire ratings and how much cover you need for your slabs, your beams. That's all in the code, and we have some notes on that as well. And then I mentioned the pour strips, so it kind of depends on the length of your garage. So for instance, this one, I can't remember the total length of this, but this one we had two pour strips, so divided up in 3 sections. So I think we had a pour strip around here, and then we had a pour strip around over here, divided up into 3s. Oh yeah, I think here we go. We can see it right here. That might be one right there. And then the pour strip also divides up the amount of concrete they can pour at once too. So for instance, they'll pour up to here and then down to here. And then there's some some unique little small stuff that detailing changes that have come up over some of our last few parking garages that we've kind of incorporated now into our new ones. Then how to become profitable on your first long span post tension parking garage. We have all of our typical details set up. You read your literature at night like Kit told us, and you say yes to everything like Tim told us. And then there are ADAP software guides and videos you can do, and then you can consult with your Orange County or San Diego senseis and gurus. Here they are down below. And that's it for now. I hope this is just a quick intro. Wanted to get your feet wet, and if you do have a garage coming up, you could reach out to us and we'd be more than welcome to help. Any questions?
Hey, John, I have a question. This is Lisa. Do you do anything to consider like the ramps in the seismic design and whether they contribute to lateral stiffness, or is it something we kind of ignore?
Yeah, so generally we do model the ramps and they're acting as diaphragms. That's because if you took it out, you'd have a big hole, right? For most garages. So yes, we usually do include them for our seismic design.
Okay, thanks.
This is Danny in LA. Is there recommendations you have regarding like shoring and reshoring periods and procedures?
Yeah. Yep.
And stressing sequencing that are associated with all of this?
Yeah, definitely. So usually on our plans, we give a little bit of some notes on the shoring and reshoring. Whatever, 30 days, 40 days reshore, stuff like that, or amount of levels. I think we do levels plus minimum to days, and then and then also yes, there's some stressing sequencing too in our typical notes too. We have all of these part of our typical details and notes, both of those. Anybody else?
Well, Danny, I have one more question, which is,
Okay.
we ever been asked to go longer span to accommodate tandem parking spaces?
The longest one, the longest one I know about is like 66.5 feet, I think. Which
And that
was,
still works with those, what's that
yeah,
beam type you were calling them, Cunningham beams?
yeah,
Yeah.
yep, yeah. So I think the normal is
Like,
usually around 62, but I think we went up to like
hmm
66.5 or something. And we did get it to work. We ran into a couple of little small detailing things, but
hmm
we ironed that out after. Now we know.
Add something on that too. Like when you get up to 66 feet, you can still use the Cunninghams, but it ends up being like, I know John was. I think you were saying 12 tendons. I mean, I think when you start getting up to like 66, it's getting to like 16 tendons. So it starts getting really crowded really fast if you start going any higher than that.
Is there a larger form of preformed beam, or do you just have to go to kind of custom PT beams at that point that use custom formwork?
I think you'd still use. I think we would still use the standard beam size for that 66 foot. Otherwise, you lose all your cost savings. I would think.
Mm-hmm.
Anybody else? All right. If there's no one else, that's it. That was a short and sweet intro version. So thanks, everybody.